I want you to close your eyes for a second and picture a hallway.
Well,
You're walking down it. The lighting is good. The floor looks like solid oak. Everything feels, completely normal.
mm-hmm.
You take a step, then another step,
Mm-hmm.
and then snap. You step on one specific tile, and whoosh, the floor vanishes. You fall right through.
It's the classic trapdoor scenario.
Right. You land in a basement. You're fine. You aren't hurt.
Yeah.
But you look up at the ceiling where you just fell through. There's no handle. There's no ladder. The hole is 10 feet above your head.
Right.
You fell in effortlessly.
Mm-hmm.
Gravity did all the work. But getting back up, that is, well, it's physically impossible.
Correct.
The physics only work in one direction.
Unless
Unless a friend up top has a rope ladder and lowers it down to you.
And that is the perfect visualization. We call it a trapdoor, but in the world of mathematics and computer science, that rope ladder is what we call a private key.
And that is exactly where we are going today. Welcome to the deep dive. We aren't just talking about abstract math or, textbook definitions. We're conducting a full-blown forensic analysis of a mathematical mystery.
It really is a mystery. We have a stack of documents here provided by a listener that analyze a very specific number, 24257, and a strange, almost haunting sequence of numbers associated with it.
It reads like a detective story, doesn't it? The course material treats this number, 24257, like a crime scene. We're going to deconstruct it, take it apart piece by piece, and see how it relates to the security systems that protect your bank account, your private DMs, and essentially the entire structure of the modern internet.
The stakes are incredibly high. We're talking about the engine room of encryption here. If these trapdoor functions didn't exist, online privacy would be a myth.
Absolutely. But before we get to the heavy forensic work, we need to really nail down the core concept. The sources keep mentioning this term, trapdoor function. We have the hallway analogy, but how does the research formally define it?
So, formally, a trapdoor function is a function, let's just call it 5x, that has 3 distinct properties. And these are really non-negotiable.
Okay, all 3 have to be there.
Exactly. First, the forward direction. It must be efficient.
Efficient meaning fast.
Efficient meaning polynomial time. If I give you a number, you should be able to crunch the math and get the result in a fraction of a second. That's the falling through the floor part. It's easy.
Okay, property 2.
The backward direction must be impossible. And I need to be clear about what impossible means in cryptography.
Right, it's not truly impossible.
No, it just means that without the key, reversing the process would take a supercomputer millions of years. It's computationally infeasible.
So it's the difference between walking through a door and trying to smash through a steel wall with a spoon.
That's a vivid way to put it, yes. But then you have the third property, which is the magic trick. If you have the trapdoor information, the private key, the impossible becomes easy again.
The steel wall just melts away.
It does. This concept was formalized back in the mid-1970s by Diffie, Hellman, and Merkle. They realized that for a public key system to work, you need math that acts like a one-way street.
And the sources highlight that there are really only 2 main flavors of these trapdoors that we use, right?
Broadly speaking, yes. You have number-theoretic trapdoors, which usually involve factoring huge numbers. That is the basis of RSA, which we use everywhere.
Okay.
And then you have something else, a different approach called lattice or combinatorial trapdoors, like the knapsack problem.
And usually these are 2 totally different worlds. You don't see them mixing at parties.
No, they usually stay in their own lanes. They're built on different mathematical foundations.
But, and here's where it gets really interesting, the analysis we're looking at today suggests that the mystery number 24257 and the weird list of data provided by the user actually bridge these 2 worlds.
It's a hybrid, and hybrids are where you find the most interesting flaws.
So let's start with the standard stuff, the Schloss or the lock. The target number is 24257. To the naked eye, it's just a random 5-digit integer, but the research breaks it down. How is this thing built?
In a standard RSA setup, your modulus, that's the 24257, is built by multiplying 2 prime numbers together. It's easy to multiply them, but hard to figure out what they were if you only see the result.
The trapdoor.
Exactly. In this case, the forensic analysis identifies the factors as 127 and 191.
Okay, so 127 times 191 equals 24257. That's simple arithmetic. But why those specific numbers? The report seemed to suggest 127 is special.
Oh, 127 is very special. It's a Mersenne prime.
I remember seeing that term. It's related to powers of 2, right?
Right. A Mersenne prime is a prime number that is 1 less than a power of 2. Specifically, $27 involved.
If you calculate $27, you get 128. Subtract 1, you get a 127.
And why that matters is because computers think in binary. In binary code, $27 is just a string of 7 ones, 1111111. It's an incredibly clean, structured number.
Huh. And what about 191?
191 is the second prime factor. Now, I want you to look at the relationship between them. This is something the source material pointed out that is really subtle.
Okay.
What is the difference between 191 and 127?
Let me do the mental math. 191 minus 127, that's 64.
And 64 is...
26 any $6.
All right.
Another power of 2.
See the pattern? We are swimming in powers of 2 here. The distance between the factors is a power of 2. One of the factors is directly related to a power of 2. That is going to be crucial when we look at the user's mystery sequence later.
So it's not just random prime numbers picked out of a hat. There is a geometry here.
There's a structure, yes.
The source material walks through this scenario called Mary's keys to prove that this setup actually works as an encryption lock. They list a public key, $8 as $80,023, and a private key, $10 as $1,887. I don't want to get bogged down in the algebra, but conceptually, how does this work?
It's all modular arithmetic. Think of a clock face. If you go past 12, you wrap around to 1. In the system, the clock is size 24257. So if I want to send you a secret message, say the number 362, I take 362, raise it to the power of the public key, the 8023, and then wrap it around that clock.
And I get a scrambled mess of a number, a cipher.
Correct. It looks like total noise. To get the 362 back, you take that noise, raise it to the power of the private key, the 18187, and wrap it around the clock again. Mathematically, it just unwinds the scramble and lands you perfectly back on 362.
And the catch is, I can only calculate that unlocking key, the 18187,
if you know the original prime.
if I know the clock is made of 127 and 191.
Precisely. That is the RSA trapdoor. If you can factor the modulus, you break the code. If you can't, the message is safe.
Okay, so that's a textbook definition. We've established the baseline. We have an RSA lock. Now let's throw the wrench in the gears. The user provided a sequence of numbers that doesn't look like RSA at all.
No, it looks like something completely different. It looks like a knapsack.
Let me read these out. We have one list of numbers, 12288, 6144, 3072, 1576, and so on. And then paired with them, we had these strange numbers, 11869, 58825, 218723.
Let's pause on that first list. 12288, 6144, 3072. What do you see?
Well, they're halving. 6144 is half of 12288. 372 is half of 6144.
They are powers of 2, specifically multiplied by 3, but the property that matters for cryptography is that this is a super increasing sequence.
Super increasing. It sounds like a marketing term, but I know it has a strict math definition.
It does. It means that every number in the sequence is larger than the sum of all the numbers that came before it.
Can you give me a simple example?
Sure. Take the sequence 1, 2, 4, 8. 4 is bigger than 1 plus 2.
Which is 3, okay.
And 8 is bigger than 1 plus 2 plus 4.
Which is 7. Got it. So that's super increasing.
Now, compare that to something like 1, 2, 3, 5. 5 is not bigger than 1 plus 2 plus 3. That's just a normal sequence.
Why does this distinction matter? Why should the listener care if a list is super increasing?
Because of the knapsack problem. This is one of my favorite concepts. Imagine I give you a knapsack and a pile of different rocks. I tell you the rocks in this bag weigh exactly 100 pounds. Tell me which rocks I used.
If the rocks are random weights, that's really hard. I'd have to try every combination. Is it rock A and B, rock A and C? A nightmare.
Exactly. It's a combinatorial nightmare. That's a general knapsack problem, and it's very secure because it's so hard to solve. But what if the weights are super increasing? What if the weights are 1, 2, 4, 8, 16, 32, 64?
Then it's easy. I just look at the biggest weight first.
You use a greedy algorithm. Does the 64 fit in the 100? Yes. Put it in. You have 36 left. Does the 32 fit? Yes. Put it in. You have 4 left. Does 16 fit? No. Does 8 fit? No. Does 4 fit? Yes. Done. You solved it in seconds without guessing.
So super increasing sequences are the easy mode. They are the trapdoor key.
Exactly. In the Merkle-Hellman knapsack crypto system, you use a super increasing sequence as your private key because it's easy to decrypt. Then you disguise it, you multiply it, and scramble it to create a hard public key that looks random.
So the source implies that this user's list is actually a knapsack key.
It suggests the user has stumbled upon a hybrid. The list 1 in 12 and 288, $644 acts like that easy, super increasing key, but it's being compared to this second, messier list, $100 and $269, $500 and $825, and that is where the forensic part of the report really shines.
This is the aha moment. I was looking at the tables in the report, and the pattern is so consistent, it's almost spooky. We have the clean number and the messy number. Let's do the math live here. 100, 288 taels minus 1,189, $279.
Okay, 100 and 288 and then $100 and $169. That is $319.
Okay, next pair. $644 minus $500 and $225.
$645 is also $319.
It's always $319. Every single step of the way, the difference between the power of 2 and the mystery number is exactly $319.
Which tells us this isn't random noise. $319 isn't just a number, it's a constant. It acts as a geometric offset. The report calls this the $319 anomaly.
So what does this mean? We have this RSA modulus 240.26.7, which we know is 127,000 times 101. And now we have this repeating $319 difference. How do they connect?
The report shows that you can actually build the modulus 24257 using a simple recursive formula based on this 319. You don't need to multiply primes.
You could just iterate.
You can just iterate. The formula is $4 and plus 1 plus 2r and plus 390.91.
Okay, so that's a linear recurrence. You take a number, double it, and add 319.
Correct. And you need a starting point, a seed.
Yeah.
The report identifies the seed as 65.
Right. So let's trace it. Start with 65. Double it, you get 130. Add 319.
You get 449.
Double 449, add 319.
You get 1217.
Keep going. And eventually you hit 11969.
And if you do it one last time, double 11969 and add 319.
You hit 24257, the modulus.
Exactly. So instead of thinking of 24257 as $127 times 119.11, this system thinks of it as the result of doubling a number and adding 319 6 times in a row.
That is wild. It's like finding a secret back door into the castle. The front door is multiply 2 huge primes. The back door is just start at 65 and keep adding 319.
And this is why the expert in me gets nervous. Because 319 acts as an error term. It's aligning the powers of 2 to fit the modulus. But here's the critical part, the part that made me gasp when I read the report.
The singularity.
It's what happens if you go backward. We know the forward direction is double it and add 319. So the backward direction, the way down the ladder, must be the inverse.
Simple algebra. Subtract 319, then divide by 2.
Yes. We started at 65, right? That was our seed. But mathematically, there's no reason we have to stop there. The number line doesn't end at 65. What happens if we apply the backward formula to the seed itself?
Okay, let me do the math. We take 65, we subtract 319. That's going to be negative.
It is. 65, 399 is negative 254.
And then the formula says divide by 2.
Negative 254 divided by 2 is?
Negative 127.
Wait, 127? That's the prime factor.
That is the prime factor. The sequence leads directly to it. If you run the recursion just one step past the start, you crash right into the negative value of one of the prime factors.
So 127 was hiding there the whole time. It was hiding in the geometry of the sequence. This proves that the linear shift knapsack system, this recursive list of numbers, is inherently linked to the factorization. The sequence isn't just a list. It's effectively a private key that encodes the factorization of the modulus.
That blows my mind. We usually think of encryption as scrambling things up so they look like white noise.
Yeah.
But this is structure. It's geometric.
It is, and it shows that if you know the offset, the 319 and the C, the 65, you can instantly break the encryption. You don't need to factor 24257 by trial and error. You just do the math, run the sequence backward, get minus 127, and you have the key.
So what does this all mean for security? The report calls this a linear shift knapsack system. Is this actually used? Is it secure?
The short answer is absolutely not. It is mathematically elegant, beautiful even, but in terms of security, it's a house of cards.
Because it's linear.
Exactly. We call it a linear Diophantine equation. In cryptography, linearity is the enemy. If a relationship is linear, like $y equals 2x plus 309.29, it's too predictable. A computer can solve that system using basic linear algebra in a fraction of a second.
So real security relies on nonlinearity, on chaos, on things that don't follow a straight line.
Exactly. So if you use this for your online banking, you'd be broke pretty fast.
Very fast.
But as a teaching tool, it is phenomenal. It demonstrates perfectly how information can be hidden. The user's source material describes a hybrid system that looks like RSA because it uses the modulus 24257. But internally, it functions like a knapsack problem using that recursive shift.
It's disguise. It's camouflage.
Precisely. And that brings us to the bigger picture. We often assume that if we can't see a pattern immediately, it's secure. But this analysis shows that patterns can be very subtle. The number 319 didn't look like a key. It looked like a random difference. But once you pulled on that thread, the whole sweater unraveled.
It reminds me of those magic eye posters. You stare at the static, and suddenly a dolphin pops out. Here, we stared at 25 or 257 and a list of numbers, and suddenly, the prime factor 127 popped out just by stepping backward.
And that is the lesson for the listener. Data often has a texture, even encrypted data. If you look at the structure, the gaps, the differences, the recursion, you find the ghost in the machine.
So we've gone from a physical trapdoor to RSA through the knapsack problem and landed on this recursive anomaly that exposes the prime factor.
A full forensic audit.
Before we wrap up, I want to leave the listener with a thought from the source material. We talked about how the secret, the 127, was hiding just one step back from the start of the list.
Yes, the singularity at TA, it will heaveny $1.
And it makes you wonder. We look at data every day, stock market trends, health metrics, just random lists of numbers in our lives. We usually only look forward at the progression, how things are growing, where they are going, but what patterns are hiding just one step back? What explains the data if you dare to run the logic in reverse past the starting point?
Sometimes the cause is hiding in the negative space of the effect. That's where the truth usually lives.
Deep stuff. That's all for today's deep dive into the architecture of trapdoors. Thanks for falling down the rabbit hole with us.
Always a pleasure.
See you next time.